recording to catch up after if they cannot attend for some reason. So it should say on your screens that it's recording now. Okay. And I will introduce George Mount to you in just a minute. Just wanted to give you a few more, sorry, let's see. Okay, let you know of a few events happening soon. So we have Microsoft Ignite, I believe happening, I forgot to put the date here. It's in September. I had it here. For those of you who are interested in, not here, there, who are, just wanted to give you the dates. Oh, this is not going well. For those of you who are interested in Microsoft technology, not only Excel, but anything else. So it's in there. I couldn't see. It's September 22 to the 24th. Usually this event runs every year in different cities around the world, and it was an in-person event. Now it's going to be online, and it's going to be a massive event. Registration is free. So if you are interested in Microsoft's technologies, not only Microsoft 365, but any other, all the other technologies like cloud and services and what else? Artificial intelligence, Power Platform, all those kinds of things. Feel free to see if there's anything happening that is interesting to you, and don't forget to subscribe. Okay, to register. So with us this month, we have 2 more sessions, one on the 16th with Paula Guilfoyle joining us from Ireland, and she will tell us, she will be presenting about tips for auditing Excel workbooks. This is such an important topic because our workbooks are no good if they are not working correctly, and we need to know and find ways of auditing our workbooks and see, test if they are really working the way they should. There's a lot of stories of companies who lost a lot of money or made bad decisions because one spreadsheet was not built or working correctly. On the September 29th, we will have Mark Proctor presenting about mastering ranges, the building blocks, there's an S missing there, sorry, of Excel. It's amazing what you can do with referencing ranges inside formulas, and not only formulas. And I've watched one presentation by Mark about this topic. I learned, it was, I think, a 10 minutes presentation, and only in that time I learned so much. So I can't imagine what he will be able to tell us in a full session of 1 hour. So don't miss that if you can. And in October, I can tell you more than I can than it is on the screen now, but you don't want to miss October. We will have a massive event in October, and that's all I can say for now. But pay attention to your inboxes, because you will be wanting to be with us. Okay, so that's all I wanted to say for now. I will keep you in the loop as soon as I can, but I can promise you, you'll be surprised. Okay, so let me stop sharing. Can you see my video now? Maybe with George? Teams is a little bit tricky because what one of us sees, it's not necessarily the same thing other people see on their screens, depending on their settings. So anyways, thank you so much, George, for joining us, for being with us today. George Mount is the founder of Steadfast Analytics, and he works as a consultant. Mostly, most of his work is related to training, and the training has been mostly related to Excel. One of the things that I see George doing, and I find it very interesting, is he prepares Excel courses dedicated to specific, very specific, how do you say, job positions. It's not that word. It will come. So, for example, Excel for nurses, or Excel for what else, George?
I just did one for Excel for nonprofit administrators. I've done a lot for healthcare things like, yeah, nurses, physicians, that kind of thing.
That's
So,
nice.
yeah.
Yeah, I think it's very interesting because Excel can serve everyone, but doesn't serve everybody the same way. So I guess it should be interesting to do that exercise of knowing, okay, so if you do this type of work, what is in Excel that you need to know? And
Yeah, absolutely. And I've got all of those tucked away in a folder in OneDrive, and anybody who gets on my list will have access to that in perpetuity and have all of those wonderful handouts and things like that.
wow, isn't that wonderful? So yeah, if you, we will send the link after the session, or where people can register to get that information, right?
Okay.
Yeah, and the files that you are sharing today is also, they will also be available, right?
Yes, they are all on a GitHub repo, and I'll put it in the chat right now, and we'll go through how to get all that stuff set up.
Okay.
Yeah.
Any questions? Any comments for now? Let us know. And I think while you do that, I'm going to turn off here my PowerPoint. We don't need that. And I'm going to ask George to share his screen. And
All right.
let us know a little bit about ourselves. So not ourselves, about you. I was going to say that the two of us, we met in person in, I don't know, maybe a year ago, was it,
It
George?
was a year ago. Yep.
Yeah, George came to Toronto and we had connected on LinkedIn, and he said, "Oh, I'm going to Toronto. Okay, so we need to go for a coffee." And so we did.
Yeah, I
We
might
met.
even have footage of that event here.
We met for a coffee, and at that time I told him, next time you come to Toronto, you let me know in advance so that you can be presenting to the meetup group. Then COVID came, and here we are. No need to be in Toronto, and that's it. So
All right.
feel free to share your screen when you are ready.
Okay, yes, I am in position
Uh,
for that. You
yeah,
know how PowerPoint likes to misbehave anytime you need to do this, hogging up all your screens,
yeah,
and never in the right order that you want. Okay.
yeah.
Uh,
So just letting you know, we have 64 people with us, which is amazing. Very happy to have you all here. This session is for all of you. If I hope each and every one of you gets some value from the session, feel free to ask questions, send your comments. Even if you have any topics that you would like to have to see presented here, feel free to drop a message there on Meetup, or even to send me an email or on LinkedIn. Feel free to reach out, okay? Okay, George.
all
Screen is
right.
yours, the mic is yours. I'll shut up and you will let you speak.
Cool. Okay. Thanks everybody for coming, and thanks again, Celia, as always, for all the stuff that you do to earn that MVP daily. So I'm gonna do my presentation. You already learned about this, so I won't go into it too much. Just to give you a sense of where I am in Cleveland, which is right here on the other side of Canada. And MapQuest, or Bing Maps, I guess, is telling me it would only take 4 hours and 25 minutes to get to Toronto right now. Problem is that the border's closed, so it's kind of a phony number. but it goes to show that, I'm really not that far from you all who are in Canada right now. It's just this pesky lake right here that gets in the middle, but we love our Great Lakes. I'm not gonna hold it against them. So that's where I am in Cleveland. I've been to Toronto several times. I have some friends up there, and I made another friend. The last time I was there, I said I had documented footage. So there we are at Tim Hortons, no less. Yeah, everybody's shocked to talk about Excel in Toronto, but I've been there, done that, and now I'm doing it virtually, and maybe I'll get to the meetup in person someday. That would be neat to meet everybody in person.
Always welcome.
Absolutely, whenever that happens. We're so unaware in this picture too. That's the other thing. Would have had no idea that it wouldn't be happening to come. Okay. So what are we going to talk about today? I want to be aware of the time, and I want to make time for questions and any kind of networking and things like that. Try to make this as participatory and meetup like as we can. So I really want to illustrate some of the key theorems and statistics that underlie a lot of data analytics and data science, and not just lecture them to you, but really make them come to life for you in Excel. So I want to be as interactive as I can. I've got, the worksheets are all set up for you to follow along. I've got demo notes, so if you want to, walk through this on your own later on, you can do so. So we'll start with normality. What makes normality so important? Why do we use that for inferential statistics? And then going from there, learning about the margin of error and how sampling works. So some of these really key concepts of statistics, how do they really work, right? We hear about them, but, do we actually know what they're doing and how they work? I think Excel is the perfect tool for doing that. The final lesson is on conditional probability. So that'll be a little different, but still very, very cool to do in Excel. We'll see if we get to it. We'll see how many of these we get to. But again, I'm going to go into how to access this stuff in a second. So if we don't get to something you really wanted me to, you'll be able to figure it out after the session, I believe. And then as far as making the most of this, just technically, if you're familiar with descriptive statistics, if you've calculated a mean or a mode or a variance, I think that'll help. If not, just kind of hold on, and I think it'll still be cool to see these things go on, and I'll try to bring some value to you. And that, as far as the Excel chops, if you're good with writing a match function or nested if statement, you should be good with this. I'm not going to do anything too crazy here, but you'll see that, with making some little hacks in Excel, we can do pretty cool things to illustrate statistical concepts. And then we'll be doing a lot of visualization because, anytime you're working with data and statistics, really important to visualize it and not forget that as a valid element of a data analysis. So let me spend a second here on this repo, just because I know not everybody's used to working in GitHub. I put this in the chat, and it's also on the meetup comments for the page for the event. So I'm just going to walk in here quickly. Here's the repo. If you're not used to working in GitHub, you've got an option here to just download everything as a zip. And I'm going to do this right now, so I make sure I don't accidentally change any of these files as I'm presenting them. So if you want to go ahead and do this with me, I'm just going to clear out my downloads here and start with a kind of fresh download so that I don't accidentally mess anything up in the master branch. So what you'll see here, actually, let me go back to this one. Everything's arranged by topic. I've got the slides here, PDF and PowerPoint. And then each of these sections you'll see, I've got the workbook, I've got the doc here, PDF'd as well, and I've got my trusty iPad right next to me, so I'll be kind of looking, these are kind of my crib notes, you can use them as well. This will just go through exactly, what I'm doing, what's going on, what to look out for when you're doing it. So if, like I said, we don't get to everything, you can pick it up from here and kind of follow along on your own. And again, if you've got 2 monitors, you're welcome to, pull up the workbook, maybe get the demo notes, whatever you want to do to make this as meaningful as possible. I do want to make this very participatory, so you'll see that all these workbooks, if it opens, will have, a starting point, and then we'll kind of walk through it and then get you to that finish point, which I'm not going to open right now because I don't want to spoil any surprises. Okay. If anybody's got any questions, let me take a look. I don't see anything, but if you do, then let us know, and we'll help you.
Just some comments here. People that are new, some people are new to the group. 4 or 5 people at least mentioned that it's their first time. And we have Gene here based in Cleveland that he says he's been knowing you for a while.
That's right.
Yeah, he's saying cheers to you.
Yeah, Gene's a double agent, being a Canadian in Cleveland, so he can kind of play both sides of the lake here.
Okay, someone was complaining about internet image being frozen. I hope this is resolved. I didn't notice that happening here, so maybe it's local over there. And yeah, I think we're good to go. No comments or questions. Thank you, George.
Awesome, cool. All right, so I probably don't have to make the case for you all too much, but there's a lot of ways to analyze data nowadays, right? There's Python and there's R, all sorts of things. Why would you even bother doing this in Excel? Well, I think that you get really hands-on. So I like this quote from this guy, John Foreman. He wrote a book on this topic, using Excel to demonstrate important statistical methods and concepts and things like that. You really do get to kind of see that, step by step. I mean, we all know the spreadsheet originated as VisiCalc, right? That was the first mass market offering, visual calculator. So it really does kind of bring that to life. It's very visual, it's tactile. You really get to see every step. It's not got that black box kind of a thing that often goes on when you're working with a programming language, which, don't get me wrong, I would strongly encourage if you're interested in getting into data analysis, picking up Python or R or something like that. But I think, we want to do this in the most logical way as possible to understanding Excel and statistics. And I wrote a blog post about this that, if you're interested in really learning analytics, and, by that, I mean, quantitative analysis in general, and this is, again, is in the deck. I will pull this up on my screen just for a second. What makes this such a potent tool? Well, a few things, first of all, is if you're trying to learn statistics or data science or what have you, okay, you have to learn how to code. All right, so you're going to do that at the same time as learning these statistical techniques. I don't think so. That's a lot of stuff to learn in one go. So this idea of cognitive overhead is, trying to break this up into more manageable learning sections, right? So we can use Excel. We all know Excel. We can use that to kind of bootstrap our way into learning more and more advanced analytics. And then, at a certain point, Excel, it gets harder and harder to, push it to get it to do what you want. Then, go into Python or something like that. So that is my case. I've got the blog post here if you want to read into that. But I'm thinking, I'm kind of probably preaching to the choir here about the virtues of Excel, so I won't push on that one too hard. But let's talk about normality and what that actually means and what normality tells us. So we're finally getting into a demo here. And I'll ask, if you wish you ever thought you were normal, well, here's your chance, because the normal distribution is really important in statistics, and we are able to extrapolate a lot about a population when we know that it falls on this bell curve, because we know exactly the spread of these values around the center. So what I mean by that, there's this thing called the empirical rule, which tells us exactly, what percent of observations you're going to find within 1, 2, and 3 standard deviations of the mean here. I built these charts in Excel, and we are going to reproduce that here in a second. But the takeaway here is that we've got a nice bell curve. And we're saying that within one standard deviation of the mean, we're going to find about 68% of those observations. We go out to 2, we get 95%. And then 3, you get to 99.7%, which, as you can see, is a very, very small amount. Not to say that it never happens. That's one of the things to remember with statistics, is that, it seems like this would never happen, but it's still, 99.7% means that it'll happen at some point. So these are the rules that we find with the empirical rule. And what I want to show you is, what does this actually look like in Excel? How does this work? What are the underlying functions and equations and things like that that actually tell us what this is doing? So let's do that. I've got the empirical rule file here. What we're going to do is use Excel's functions for probability mass functions here. And those are going to tell us what percent of observations we're going to expect to find for some given value in our distribution. So for example, let's say that you have a variable with a mean of 50, standard deviation of 10. We know it's normally distributed. If we know that information, then we can use the probability mass function to say that 3.7% of observations are going to equal 54. So this is going to, give us that breakdown of what we expect values to take on in that distribution. So let's look at doing that in Excel right now. I'm going to open this up here. And okay, there it is. That's good. All right, so we already covered the empirical rule. Now what I want to do is bring this to life here. So I'm going to go to my demo notes, and you're welcome to follow along. And I will kind of walk through how this works. So what I've got here is a normally distributed variable with a mean of 50 and standard deviation of 10. Those are the two parameters of a normal distribution. Then I've got the numbers 1 through 100 here. So what I want to know is, what percent of my observations would I expect to be a 10 or a 15 or a 16 or whatever? And the way that I can do this in Excel is with this norm.dist function. So I'm going to start my function here. It's going to be norm.dist. There's going to be 4 arguments we need. The first one is going to be x, which we have over here. This is just the value that you're interested in knowing that breakdown of. And then I need to know the mean and the standard deviation. I've got those up here. Go ahead and lock those in, since we'll be popping this formula down the column. Our last option here is whether we want this to be cumulative or not. If we were to do cumulative, it would essentially tell us, all the numbers from 1 to 5, for example, for column 12. We're just interested in going row by row, right? We don't want to do like a running average or a running sum, I guess that would be. So I'm going to set this to false. And now we can see that, this number is really small. We're saying that, well less than, 1/10 of 1% of a time would we expect to find a 1. So let's try to fill this out and see if we get more common values as we get closer to 50. I'm going to do that. And you can see I already have these set up. These are area charts over here. So I just figured, not getting into that, really focus on what's going on over here on the left. And now I can see exactly, as I scroll down here, we get more and more likely to reach a 41, right? 2.66% of the time we would expect an observation to be a 41. And then, go all the way down to the bottom. And again, then it gets very, very unlikely again. So what I'm going to do now is just this entire set here, and I'll go down to my status bar. I love to use it. I hope you do too. Come down here and we'll see that these all sum up to just about 100%. Of course, it's not 100% because a normal distribution could take on any value. You see that, you may have heard of long tails, right? And that's the thing with the normal distribution is this just keeps on going. It's very unlikely to get, a value of 500 or something like that, or a value of negative 100 or whatever, but it could still happen. So I think this is one cool thing that we're actually seeing, with our eyes, right? That probability mass function, I can sum this up, get very, very close to 100 when I'm dealing with, a mean of 50, standard deviation of 10, numbers 1 through 100. It's going to fall in this range overwhelmingly most of the time, but not all the time. So now what I want to do is kind of bifurcate this, and we're going to use conditional logic here to break down exactly how many of these values fall within 1, 2, and 3 standard deviations of the mean. So we'll do some setup here, and all I need to do is set up my boundaries essentially. So I'm going to find, what's our range from 50 within 1 standard deviation of the mean from that. I'm just going to do my mean, and then I can just subtract that to standard deviation times C4. I have my font really large, so it's harder to click in the cell, but we got it working, so that's good. So we have our lower bounds here, and now I can just do the same thing. Let's just turn that into a plus. And there we go. Obviously, I didn't do something right there. Now it's working, and let's just bring this over. So what I'm saying here is that within 1 standard deviation of the mean are all the values from 40 to 60, 30 to 70 for 2, 20 to 80 for 3. So we're kind of getting, what are the ranges within which these standard deviations fall. Okay, and now what I need to do here, so I know all of the values between 1 and 100, I just need to use some conditional logic to, find out which of these values fall within, between 40 and 60 and so on and so forth. Okay, so I'm going to do that now. Let's do if and, okay, I have A36 there, but I think it would just be A8. Let's do that. All right. Okay. Greater than equal to, actually, I think it should be greater than or equal to, but I think I have it wrong in the demo notes, but we'll get through this. Greater than or equal to that. I'm going to lock that in. And then A36 again, or A8 in this case. Less than or equal to C6. Lock that in. Okay, if it falls in that range, right? If it's greater than or equal to 40, if it's less than or equal to 60, then we are going to include the value. Otherwise, no. Okay, so I'm going to just drop that in here, and we can see that all of the values from 40 to 60 in this case, we kept those. We didn't keep those because these don't fall within our range, but these do, right? So let's just format that quickly so it's easier to look at. Not that way. There we go. And I'm going to just turn that into a percent. Let's bring out the decimals because you saw how small some of these numbers can get. And now I can see that, here are all of my numbers between 40 and 60 and the percentage likelihood that we're going to meet those values. So now what I need to do is just complete 2 and 3 standard deviations, and I can just, copy and paste these now. And we get this kind of triangle thing looking, right? Where, within 1 standard deviation, that's the values between 40 and 60. 2 are between 30 and 70. 3 are between 20 and 80. And you see that over here, I don't know what's going on with these charts, why they don't look right. Maybe I did something out of the ordinary, but let's try something first here to troubleshoot this. What I'm going to do is just sum up all of my values within 1 standard deviation of the mean here. And what I should see is that it is, okay, so 70.64, so that seems a little high. So let's see what I'm doing wrong here. Maybe I do need to make it a less than. Let's see if that fixes it. All right, greater than, less than, let's do this. And now let's see. I don't know why those charts aren't looking the way I want, but we'll figure it out. If I can't figure it out, then I'll just go to the finished workbook. That'll have our answer. So now we could see that within 1 standard deviation of the mean, that is approximately 65%. That's what we said the standard deviation. Within 1 standard deviation, we'd expect about 65% of the values. I'm going to go ahead and go over to a finished workbook just so we're not playing with live ammo anymore. And now let's go ahead and take 2 standard deviations of the mean.
George?
Yes.
There's people here. So here, Rajiv is saying upper bound is incorrectly locked.
Okay.
It's locked to C6 incorrectly.
Yeah, that's why I went down to the finished example here, just to, so we
Change
eliminate
to
that.
C6 with $ for C and for 6. That's what he's suggesting.
Okay. All right. Well, I'll stick with this one so we know exactly what's going on here. And then I think what I want to do is set this to greater than or equal to. Do that.
See.
And there we go. All right. I think we're good here. So these charts look good to me.
Yeah, now they're looking, yeah.
That's good. Thanks everybody for the real-time cell checking here. Never know what's gonna happen when you're doing live coding, right? So that's why I have the finished
Don't
worksheet
worry.
here.
There's one hand reason, Angie. I'm not sure if you want to ask something. Feel free if now that we have the opportunity, or if that's a mistake. I don't know. Sometimes people click to raise their hands and they. So let us know. Yeah, maybe that's not important for now. We'll wait. Go
Okay,
ahead,
yeah, I've
George.
got
Thank you.
a
Yeah.
sure. Oh, please, yeah. Thanks everybody for the for your patience as I got this up and running. But I think we're good now. What you're gonna see, and it looks like I need to update one of my screenshots in the demo notes. But what I wanted to demonstrate here is that within 1 standard deviation of the mean, that's all the values from 40 to 60. I'm gonna sum that up. We know that that is about so 70%. Should be a little less. 99, 95% within 2 standard deviations of the mean, and then 99.7 within 3. Okay, so that is how we can really see the empirical rule within Excel. We're using this norm.dist function here, and using these. This is a pretty cool function, right? Because for example, what if I were to change my standard deviation to 20? You can see that we get a much wider kind of a range here, right? Because there's a bigger value, bigger range here. It goes from -10 to 110. Before it was what was it? Yeah, 20 to 80. And again, I could shift the mean. Then we can see obviously that that's going to shift, and our charts get not great now on these values. With I'm not going to be capturing as much with the mean of 20. I sum up these values, and we're only picking up 97.5% of those values now. So that is how we can really see this principle come to light here in Excel. So thank you everybody for bearing with me with my technical difficulties, but I think we got this up and running. So that is good. I'm not going to save this because you've got all this stuff in the repo. You can download that at your time. Okay. Yeah, let's do one more and then we'll go for some questions because I know we've got I don't want to spend too much time just lecturing at you, but I want to get through a couple of these. Okay. So let's do, now that you kind of understand how the normal distribution works and what percent of values we would expect to find within a given range, we're going to move on to its relationship to statistical inference. So you'll see that the normal distribution forms kind of a missing link between our sample and our population. And the way that I'm going to demonstrate this is with roulette. This is the European roulette wheel, I believe, that has values between 0 and 36. And what I'm going to do is use that to simulate a game of roulette here in Excel. So what I'm going to do is, first I will simulate 500 rounds. I'm going to plot that as a histogram. And then I'm going to simulate it 100 times, take the average of that 100 times, do that 100 times or 500 times, and plot that as a histogram, right? So one time we're just taking, 500 rounds. The second time we're going to do 500 rounds of 100 times and see, what is the difference in those distributions? What actually happens when we do that? So this is going to be the central limit file here. And let's do that. So like I said, first we'll simulate those 500 rounds and plot that distribution. All right, so I've got the histogram set up and everything. Just figured we'd kind of eliminate steps here. And rand between is going to be our friend here. There's some new ways to do random values with a rand array and things, but we'll keep it old school for right now. And I will do rand between 0 and 36, right? Because I just want a random number between 0 and 36 to kind of mimic what a roulette wheel does. And now all I need to do is just do this 500 times. Okay. If you're not familiar with generating random numbers in Excel, we'll go through that quickly here. So every time I recalculate this, we'll get new numbers. You can use F9 on your keyboard, or if you want to go over to formulas and calculate now, you can get through it there. F9 again is the shortcut. But the important thing I want you to see here is that we've got an equally likely chance of getting any one of these numbers, right? So, it could be a 26, just how so happens this time I get 2 in a row, not too likely. We're equally likely to get a 0 as we are 36. This is called a discrete uniform distribution. So we're just going to take 500 of these, and each time, these boundaries change sometimes just by default with Excel, but you see that rectangle kind of a plot here, and you know that we've got a uniform distribution. So now what I want to do is, and you see that, I'm going to simulate that spin 100 times, take that average, and then do that 500 times, okay? And see, do we get something different when we do it this way, and why? All right, so I've got this one set up a little better. What I'm going to do, again, take that average. We'll do this 100 times 500. Again, ran between 0 and 36. Go ahead and bring this over to 100 times, and then I will bring that down. So again, I've got a bunch of random numbers here, and I can use F9 to recalculate. I can go up to formulas and recalculate. And you see that we've got the average over here. And now we've got something pretty different looking. So in this case, we have that rectangle look, right? Where it was just equally likely to get any of these numbers between 0 and 36. This time, I've got more of a bell curve, which should be familiar from the last section. This is a normal distribution, right? So what we did is take a sample mean. We did this 100 times. We took the average. We did that 500 times and plotted all of these sample means and see that these look normally distributed. So the moral of the story here is that any variables sampling distribution of the mean will approach normality if that sample size is large enough. And that's the really important terms and disclaimers here, is if your sample size is large enough, right? That is going to be the focus of the next section. I will do that, and then I guess we'll pause for questions because the next one is kind of intensive. I think these two, the central limit theorem and the law of large numbers, are best paired together. So I will go ahead and continue on with that. But I definitely, if you've got questions, feel free to drop them in the chat now or what have you, and we will get to them in a minute here. But this is the central limit theorem. And again, I hope you can see, exactly this ability to just go in here and recalculate these numbers and see these kind of change right before your eyes. It would be a lot harder to rig this up in places other than Excel. And, we're really getting to see exactly, what is a central limit theorem? Oh, okay, well, I've got a distribution that's uniform, but when I take the sample mean, it's normally distributed, given I have a large enough sample size. And that's the really important disclaimer here. And that's what you're going to see a good rule of thumb in knowing when your sample size is large enough in this next demo. So I'm going to go ahead and close out of that. And I'll do one more, and then we'll take a break here. Well, not a break for questions, I guess. Okay.
So there's a comment. Your examples show X to be integers. Any difference when X is real number? For example, heights, weights, when you can have fractions?
Yeah, it really should not matter. So I mean, height and weight would be examples of normally distributed variables. And, in that case, if you were to work with a normally distributed variable and find the distribution of sample means, it should also be normal. The nice thing with that is that you're going to need a smaller sample size to get to that, normality of sample means. And then, yeah, fractions, we were using a discrete uniform distribution, but, if we were to use the rand function, right, and just get, random fraction numbers, it would work the same. Again, the important part is knowing that you have a large enough sample size, and there's a lot of there's some guesswork. There's some more robust things that you can do to know that your sample size is large enough to perform statistical inference on it. We're going to look at kind of a nice rule of thumb to understand, what makes a good sample size. And I'm sorry, I'm just jogging between slides here to figure out where I have that information. But we covered this one. So if the sample size is large enough is the important part. How large is large enough is probably the question that you're asking. Some people say it's 30. You need a sample size of 30 to have a large enough sample size to perform inferential statistics. Some people say it's 60. Some people say 100 is even better. Like I said, it kind of depends on how normal your sample is. So going back to that question on, can we do this with heights or weights or something like that? Those tend to be pretty normally distributed. So you don't really need as large of a sample size for the central limit theorem to kick in. If you have something like roulette throws where they're totally not normal, they're uniform, then a larger sample size is better. So let's take a look at doing this in Excel again. I'm going to go back to my roulette example, and I want to know what my average spin is given more and more spins. So I'm just going to take kind of a running average and then plot that, and then, using that random number capability, see exactly what happens. Let me go back to this and law of large numbers. Here it is. All right. So I am going to go back to the board here, and first I want to find the result of one roulette toss. So let me do that here. All right. Again, that's just going to be rand between, get a number between 0 and 36. So you've seen that before. All right, so there's our function. Okay, and now what I want to know is just to take a running average. And you know what? We don't need to sum it up. We're just going to take this running average right now. I want to know what is the average from B3 to whatever my other row is, right? Oh, not that. B3. Okay. All this live coding gets me into trouble. All right. So we have this. What I'm doing here is just taking a simple running average, right? So at 3 spins, I got a 24, a 12, and an 11. That brings me to an average of, 22.33. And again, I can put that down here at the status bar. As I take more spins, our average changes. So each time, this average is kind of converging to what we're going to call our expected value. And the way we're going to see this is with a simple line chart. Looks like I need to insert it this time, but that's fine. Okay, so there's our cumulative average of spins. I am going to just recalculate this a few times to give us a flavor of what might happen. So you'll see that, every time is different. Sometimes we start at a really high number. Sometimes we start at a really low number. Sometimes it, converges kind of quickly. Other times it's harder, or, it takes a little longer. But, the important takeaway here is that no matter what, we usually get to a value of about 18. And again, if I went to look at all the numbers, we could see that we're pretty close to 18 right down here. This is called the expected value, right? Because, over time, we have numbers between 0 and 36. We would expect that, the average of that would be 36 and or 18. And we're actually seeing that, given more and more of these hypothetical spins, we're getting to that. And again, you can kind of see where these rules of thumb come in with sample sizes. So here's our number of samples down here. I'm at 30 right now. You can kind of see that, we start to get to a leveling off point at 18 there, right? And then, 60 is kind of one of these other ones that we see that it seems a bit more stable, but there's still some volatility. And then we get to 100 and it looks pretty steady. It kind of stays at a good steady state of 100 that whole time. And, this is just a rule of thumb. There are, other ways to know how big of a sample size you need. But I think that, again, this example with not a lot of setup here in Excel, we're able to simulate this to a pretty satisfying effect that would be really hard to do elsewhere. And I can just kind of go through this and see exactly, where are these rules? Why do people say that sample size of 30 is a good rule of thumb, or sample size of 100 or whatever? We can go in here and say, okay, because of the law of large numbers, I know that, we are going to expect to find this population mean. And then the way that these pair up, all of the demonstrations that we've done thus far, is that, if we know where our mean is, right, and this is our expected value, we know the distribution of points around that mean, which we found with the empirical rule, and we know from the law of large numbers that any variable with a large enough sample size is going to have that normally distributed shape. So that's how all of these things that we just covered kind of work together in being able to let us just take a smaller sample and infer parameters of a population given that sample, because we know what to expect. We know that we can expect a normal distribution. We know that we can expect an expected value here, and we can kind of make probabilistic claims about a population given a sample. So I think that's pretty good. We still got some time, but I want to jump into and make sure that everybody's got time for questions and all that kind of thing. And then maybe we'll do a couple more, and I think that'll be good. How does that sound, Celia? Awesome. Okay. I'm going to
my
pull
mic was off, sorry. Yeah, go ahead, George. We still have time.
Okay, great. Okay. All right, I'm looking at the questions now. Okay, sample size, I think we covered Rajiv, so that's good. Does it mean when you keep betting on 18, then you must win in the long run? Trying to think if that's true.
I think the average of the results will tend to 18, not.
Yeah,
not
right, because each one of
necessarily.
those is kind of an independent event, right?
Exactly.
So yeah, that was a good
So
brain teaser. Yeah.
yeah, so when you sum and divide by the total of experiences you've made, the result of that, which is the average, will be closer and closer and closer to 18. But it's like you say, each event is independent from the other one. So you can keep betting on 18 on any other number, and at some point you may get it. It's like the lotto, I think, right?
Yeah, exactly. Yeah. If you don't all know, Celia used to be a math teacher, so she's got my back here.
Don't count on that. Okay, go
Okay.
ahead.
Okay. Thank you, Bella. Yeah, that's the normal curve. Yeah, exactly. It's kind of depending on your distribution and the percent likelihood of getting each of these values. Okay, Celia's got my example. Can you give me some examples where I can put this use in our daily work? I think the next example might be really good for that because I have a data set of housing prices, and we're going to see, given a larger and larger sample, how your margin of error drops. So it's a good example in the importance of your sample size and what the margin of error means, which is a pretty commonly reported statistic. Okay, so there's that. Thank you there. Keith. Okay. I think there was some debate about that question, and that was a good one.
We have Angie raised the hand, Angie Wong. So if you can.
Yeah, thank you, Vivek. Angie, I asked Angie before, and we didn't get an answer, so maybe it's a mistake, the hand raised. But if there's a question or comment, please feel free.
I'm not familiar with Nick Leeson, so I'll have to look that one up. Yeah, okay. How do you define a sample size to be 30, 60 when you say it depends on whether it's normal? How do you define normal? That's a good question. So there are some rules of thumb that you can do. For example, we've been plotting histograms, and that's just one easy way is if we plotted, for example, if I go back to the central limit theorem example, I'll pull that up for a second. And if you were to plot a histogram and it looks like this, then the chances are that you've got a normally distributed variable. There are some other ways to do it. You can look at some descriptive statistics called the skewness and kurtosis, and there are some ways to do that in Excel, actually. Skew.p, I think, is a skewness of a population, but we're not dealing with a population, so it's more conservative to use the sample one here. So if I could just take the skewness of this and the kurtosis of this, and let's do that too. So these are two measures that you can use to assess how normal your data is. The closer they are to zero, the more normal, so to speak, you would think that they are. And in this case, you can see that they're really, really close to zero. So that's a good indicator that we're dealing with normally distributed data. There are some other ways you can actually use inferential statistics. There's something Shapiro-Wilk test, and there's some other ones where you can find, how likely would you expect to find this distribution of variables, compared to a perfectly normally distributed one. So this idea of a normally distributed variable is kind of like a, lab creation, right? I mean, we use it as a model, but when we go out into real life, it's not like any variable is ever perfectly normally distributed because it's real life, right? Things don't always follow exactly how they do theoretically, but we can use some of these rules of thumb, like looking at the skewness kurtosis, visualizing it, running a Shapiro-Wilk test, and that can kind of tell us whether this variable is close enough to being normal. So I hope that didn't confuse anybody too much, but I think it's a good question and a really good consideration that, when we say normally distributed, no variable in real life is ever going to be, like perfectly normally distributed. I mean, we were using the empirical rule, and I apologize that example didn't go as well as the other ones, but I think you can go back to this one and see exactly what a normally distributed variable looks like. We see that it's just a beautiful, perfect bell curve here, but then when we get to real life data, and this is even simulated data. This isn't even real life data, but even simulated data does not look exactly as, you know, gorgeous as that bell curve that we made. So I hope that kind of answered your question. I think the next example will help as well, kind of explain how all this stuff works together. Okay? Yes, IQ. Representative sample, exactly. Yeah, that's a whole other can of worms that we haven't gotten into, which is the, you know, before we go off and analyze it, we want to make sure that it was collected right in the first place. So we just got to assume that part, and that's going to be a really important part of this next example. So I think what I'll do, because it's already 6:30, I'll go through this one, and then the last one is pretty time consuming, so it's probably best if you check it out on your own, but it's a really cool example that I think you'll enjoy. Okay, so we talked about the law of large numbers, went through some questions, that's good. So let's talk about sampling, which fits in well to Oakley's comments, and look at the margin of error. So, you know, we in the US are heading into an election, and we might hear things about polls, and we might hear that there's a poll with a margin of error of 2 or 3%, right? Plus or minus 2 to 3%. So what does that actually mean? And what does it tell us about sampling and samples and populations? So let's do that now in Excel. Wrong slide. Let me pull up the margin of error slide here. And we'll do this one, and then I think we'll take any last questions or comments or whatever. Have some meetup vibes going, and that should be good. Okay, so what does a margin of error actually mean? Well, we're going to be dropping some equations and things like that here, so I hope you can bear with me, but it'll be worth it. So what we're saying here is that our margin of error is going to tell us how much uncertainty there is with what the population mean really is. So again, if one of the central ideas of inferential statistics is that, you know, we have a sample of data. We want to know about the population, so we need to make inferences about that population using our sample. And, you know, in theory, the larger the sample you have, the closer to that population you should be. Again, that kind of assumes that your sample is actually representative and there's no bias in the way you actually collected that data. So that really goes more into the way you collect the data. So we'll kind of leave that off the table for right now. Just assume the data we're working with was collected representatively. But what you'll see from this chart is that, you know, the larger and larger of a sample, so we've talked about sample sizes here, the larger and larger of a sample you get, the tighter your margin of error. So let's say that we think that our population is going to be at 50%. You know, if we only have a sample size of 96, then, you know, we're going to have to report a really, really large margin of error. You know, we're basically saying that, well, we think that is 50%, but, you know, it could be 60%, could be 40%. We don't really know. The more and more sample size we collect, we're getting tighter on that estimate. So, you know, if we get up to 2,400, we're saying, okay, well, we think it's 50%, you know, it could be 52%, could be 48%. We still don't, we never ever really know what the population is. But in theory, the more sample size we get, the tighter that margin of error should be. So let's look at how that plays out, and let's look at where does this rule of thumb of that 2 to 3% margin of error really come from, because that's one of those things that's often used. You know, people just kind of assume that there's a 2 or 3% margin of error, but what I want to show you is why do we say that? You know, what makes that kind of that gold standard of margin of error? So let's do that one here. This is a real life data set of housing prices. So going back to this example of, you know, when might you use this in a finance function or something like that? Let's say that you're pricing real estate and you've got a sample and you just want to know, you know, what is the margin of error? So you really, you know, what is our uncertainty of the true population, you know, housing price mean? You can do this. Oh, I cheated there. But pretend you didn't see that. We'll do this. We'll run through this one. And then I think that'll be a good capstone. So I appreciate everybody staying on extra here. I hope you're getting something out of this. And yeah, let's run through this. So first thing I want to find is the sample mean. Again, we have approximately 550 housing price observations. I want to find what is our running average. So I'm going to do this pretty similarly to what I did in the last example, where I'll take it from B7 to B8, and I'm just going to continue to get that running average. If you're curious, what I've done with these functions here is I'm using the formula text function, and I just wrapped a if error around it. So essentially, it's just going to be blank until I pop a value in here, and then it lights up. So hope you can use that in your training. I thought it was kind of cool. So let's find the standard deviation. So again, I found the sample mean. And again, we would think that the more and more sample that we get, the closer we're going to get to the expected value. Same idea as with the roulette example. So I'm going to do that. And now I need to find the standard deviation, because we're going to use these numbers to, again, find exactly what is the boundary around our proposed population mean. So let's do that. And again, I've got all the equations and things like that. I don't want to get into them too much, but just so you can kind of follow along if you're not familiar with some of these functions and things like that. But I'm going to find the standard deviation. And again, this is for a sample. We do not have the population. So it's better to use the standard deviation of the sample. I am going to, again, do kind of a running standard deviation here. So if I go from B7 to B8, we'll see exactly how that kind of trends with more and more of a sample size. You'll notice that I didn't calculate any of these up here, and the reason I chose not to is that the whole idea of standard deviation or variance is how do multiple observations vary from each other. If we've only got a sample size of 1, you can't really even calculate a standard deviation, because there's nothing to deviate from, because it's only one observation. So that's kind of another food for thought here, is that do you really have a standard deviation if you've got a sample size of 1? You really don't. Same with the mean, I guess. So let's find the standard error. And the standard error is going to be a measure of our uncertainty about the population mean. So I'm going to take our standard deviation. I'm going to divide that by the square root of our sample size. So you'll see that with our sample size, as that increases, our standard error is going to decrease. So again, the more and more of a sample size we have, in theory, that should mean the less and less uncertainty we have about our population. So that's why our standard error is going to go down. You can kind of imagine that, as our sample size goes up, we're just tightening this curve here. And now what I want to find out is this margin of error. So we're going to calculate this using the critical values. And then we'll ultimately find our margin of error, which is, again, exactly what is the boundary around our proposed population mean. And we'll calculate that as a percentage of the mean here. So the way I'm going to do this is I'm still using VLOOKUP, don't hate. I'm going to A8 here, go to my critical values. And again, since we're dealing with such small sample sizes, we're going to be more conservative in the critical values that I'm using here. So if you're familiar with critical values, effectively, these are giving us, what is the boundary around which we would expect to find, a less likely sort of population. I'm going to look that up. Let's get 2 here. And that's fine. I think I actually wanted a true there. Yeah, I do, because we wanted an approximate match, because we don't have all of the values, right? We've got some of these that aren't actually going to be found in that critical value table. So let's do that. So we'll see that, as we get a larger and larger sample size, our critical value goes down, again, because in theory, the bigger sample size we have, the less uncertainty we're going to have about our population. We can use a lower critical value. All right, so with that, let's calculate the margin of error. That is going to be F8 times E8. That is this function here. So critical value is denoted here by Z. We're going to multiply that times the standard error. And what you're going to see is that, again, you know, the more of a sample size we have, the lower this thing tends to get. So now all I need to do is just calculate this as a plus or minus percentage error of the mean. So what I'm saying here is that, you know, when I have a sample of 6, my mean is $50,000 approximately. And I think that the population mean is going to be somewhere $11,000 within that. So it could be, you know, we have to divide this by 2, but it could be approximately, you know, $6,000 less. It could be about $6,000 more. So this is giving us that kind of boundary around our estimated mean here. So that's how these work. And you'll see that, you know, as we get larger and larger of a sample size, this margin of error really constricts, so that I can say, you know, my mean is about $68,000. I think there's about $22,000 in, you know, a margin of error to actually get the population mean. So that's what we're going to do to represent this graphically. And the way I'll do that is divide our margin of error by our sample mean. So again, that's the margin of error as the percent of the mean. And then I just need to divide it by 2 because, again, we're interested in differences greater than or less than. So I kind of have to slice that in half. And so you should really think of this as plus or minus 9.4% of the mean. And then let's do that. So then you'll see here exactly that, you know, our margin of error over time goes down. Again, you can kind of see these rules of thumb. Once I get to a sample size of 100, you know, it goes to about 4%, so on and so forth. It's probably better to look at this graphically. But over time, our margin of error goes down to about 2%. It actually is a little lower. I think, what does it get down to here at the bottom? Yeah, 1.6%. But this is what this 2 to 3% margin of error actually means. So we're getting you know, we have a sample and there's some error around where we think our population is going to be. So this is your margin of error that we actually know, you know, what percent sampling error is there for that population. So that is what the margin of error is. And this is how, again, you can actually really see this, you know, over time. How does our margin of error change and go down and get to that, you know, 2 to 3% kind of a range. So I hope that was helpful. I'm going to stop everything here. And again, all this stuff is saved in the repo, so don't worry, don't freak out if I'm not saving something. It's all saved in the repo. So let's do that. And I'm going to end my screen. Yeah, okay, so thank you, Natasha. Oh yeah, thanks, Gene. I know somebody had mentioned that too, about making sure I say Z, but yeah, missed the cue on that one. Margin of error depend on the confidence level. Yes, so we were assuming a 5% confidence level. And that kind of relates to this question from Rajiv about z-distribution critical values. Essentially, what I was doing was taking a critical value table, and for very small values, right, when we had a very small sample size, you just wanted to, yeah, exactly, use that z-distribution or z-distribution, I remember this time, so that you're being kind of more conservative with the sample size and that critical value. So good questions, everybody. And that's it from me.
Thank you, George. That was a big lesson. I mean, a great statistics lesson. Thank you so much. And if you want to turn on your video cameras.
I have one question, Celia.
Yeah, go ahead, Vivek.
So how do you, like, you know, we have seen so many, like a marathon of statistical analysis, but do you have any example on DOE, like design of experiment, how we can prove the hypothesis, you know? In statistical analysis, you have a design of experiment. So do you have any example on that?
Yeah. can't think off the top of my head, no, but it's a good question. There's got to be something cool out there.
Yeah, actually I was challenged with one of the DOE experiment on proving hypothesis, and they asked me to do Excel modeling, and I had no way. Even though I'm on statistic a lot, but I had no idea to how to create a model in Excel, and I don't have that idea yet.
Yeah, that sounds like a cool project. Maybe you'll do a presentation on that. Well, I'm sure.
We'll invite.
Celia tells me how much you do behind the scenes, so maybe not.
Yeah, I guess it's a good opportunity for you to connect and see how you can find an answer for that.
Yeah, that's true too. I've got my contact on the meetup and on the slides, and I'm easy to find. So please.
Did you finish your presentation, John? Because I hijacked here the screen, but you maybe still had some slides to go through.
I'm fine.
You? No, do you?
Yeah, I'm not going to all of them.
No, you please feel free. Just share your screen, and then I'll share mine again. Do you have some more information to present?
I don't think so.
No? Okay.
Yeah, I'm good.
It's time for a group photo.
Vivek, you look like a teenager.
Well, I'm reversing my age, so
Yeah,
been working a lot.
I'm working on my COVID Santa Claus look.
Where's everybody? There's 60 of us. I can only see like 10% of that on the screen. The more people turn on the video cameras, the more seats we will have, and we will show. Hi, there's Mark.
There's Shy.
And Oakley. Yeah. Thank you so much for joining us. And who else? Any other questions you would like to make? How did you like the class? There were people saying they love the content. Some people already had to leave. I know that a lot of there's always people attending from the other side of the world. For them, it's late or early in the morning. So we do appreciate that. It's so nice to see you. It does make me feel a little bit like we were together in person on a session in person. And that's how I see students behaving if teachers decide to use the all-together mode and to teach a class on Teams. That's what's going to happen because everybody will act funny. Or maybe
I'm last bencher, so I'm allowed to do that.
Yeah, or maybe not. Maybe
all the smart one is in the front row.
No.
Or maybe this is so normal for kids that they don't even care about. It's just for us.
I was always in the hall. I don't remember ever being in this.
We have a plant here.
Where did that come from?
Yeah, that's a plant.
Oh yeah.
Someone wanting to be here. Oh, they want to.
Everyone want to play poker?
What's that?
Poker set.
Okay. So it's a good time to finish our session today. If you have any questions or any comments, it's still time for that. Let us know. Otherwise, George, I'm glad that at some point you didn't have to do the 5 hours almost driving, but if you can at some point, let us know. It will be different to have you here in person. And like I said, beginning of the meeting, for those who weren't here, we have awesome content coming in. Mark is over there in the front row. He will be presenting end of September, the 29th, if I'm not mistaken. And Paula Guilfoy, MVP, she'll be presenting next time on the 16th. Yeah. And in October, we will have a special session that I will be telling you about soon. So stay tuned for that. I think we're good to finish our session. Keep your eyes on your email because I'll be sending the video recording and link and all the materials from George and the way you can get in contact with him. Where's the best way to find you, George? The best
yeah,
social
maybe I
media
should share
or
my screen.
yeah.
Oh yeah, I should. Oh, thanks for reminding me. I should have taken you up on that. Okay. Let's see if I can salvage this. All right, you can find me at any of these places. There's my websites. The stuff is on GitHub, so that's good. LinkedIn's good. I'm pretty active there. If you are so inclined, you can head to the site and get all of these workshops. I've got, learning objectives and a lot of notes and stuff like you saw today in the files, all the cheat sheets and stuff like that will all be in that resource library. If you're interested, here are a couple of books if you're kind of interested in this idea of using Excel for statistical analysis. This is a good one. And then this is the guy I talked about at the beginning, kind of teaching you a lot of these data science algorithms right from Excel, which is a pretty cool view into how they all work. So thanks for reminding me, Celia. I forgot
You're
I had that
welcome.
important stuff at the end.
Yeah, it's
But
important
it's
to know.
there.
And Brent is recommending your data camp course.
Oh, good. Yeah, perfect. Yes, I will.
Right.
I will put the repo in the chat too again, so that everybody has that.
Yeah.
Okay, here's that. And
is it an online course that people can take anytime?
the one at Data Camp is actually, yes, and I think they're free this week, so this would be a good week to do it.
Okay.
Yeah.
So that's great.
Amazing. Okay. Well, thank you everybody for doing this.